So if you try to increase the flux through the loop, induced field will oppose that increase. Another example, suppose the north pole of the magnet is taken away from the coil. That time flux passing through the coil will be withdrawn, it will decrease. So coil will generate its own magnetic field which will try to oppose this decrease in the magnetic field or magnetic induction. So it will generate its magnetic field which will be in the direction of original magnetic field due to the magnet. So in doing so, it will generate EMF, and that's why induced current will flow through the coil. So if you try to decrease the flux through the loop, induced field will replace that decrease. So this is Lenz's law, which states that the direction of induced current in a circuit is such that the magnetic field produced by the induced current opposes the change in the magnetic flux that induces the current. There is another picture. Again, it will clear the idea of Lenz's law more. We have a magnet. South pole of the magnet is facing the coil, and here is the coil. Ends of the coil are connected to the sensitive galvanometer. South pole of the magnet is moved towards the coil. On account of electromagnetic inertia, it will try to oppose the approaching magnet. If it has to oppose the approaching magnet, then in that case, face of the coil, which is facing the south pole of the magnet, should act as a south pole. And we know that in case of a current carrying coil, if the current flows in clockwise direction, then in that case, that face of the coil acts like a south pole. So that's why south pole of the coil will oppose the approaching movement of the south pole towards the coil. So that time, the deflection produced in the galvanometer will be on one side of 0. Now, when the south pole of the magnet is taken away from the coil, then in that case, the magnetic flux passing through this coil will be withdrawn. So coil will try to oppose that decrease in the magnetic flux. How will it decrease? How will it try to oppose? It will try to attract the south pole. And for the coil to attract the south pole, the face of the coil, which is facing the south pole, should act as a north pole. And for this to act as a north pole, anticlockwise current will be generated in the coil. Now here we can see that the direction of the current flowing through the coil is reverse, and that's why deflection produced in the galvanometer is on the reverse side. So coil will generate its own magnetic field, or it will generate its own EMF or induced current, which will try to oppose the relative motion between the coil and the magnet, and it is opposing the change of flux passing through the coil. So the induced field in a loop will oppose the change in the magnetic flux through the loop. After that, next topic is AC generator. This you have already studied in 10th standard. Simple construction. There are two pieces of the magnet, and in the uniform magnetic field, the coil is rotating. When the coil completes half rotation, current will flow through this circuit in one direction, and after it completes half rotation, the current will flow in the opposite direction. So direction as well as magnitude of the current will change. And why is the magnitude of the current changing? Because area of the coil in the magnetic field changes. That's why magnitude of the current will change, and even the direction also change. AC generator produces a time dependent EMF which is given by the formula E is equal to E naught sin omega t, where E naught is the peak, that is maximum value of the EMF, and omega is angular frequency of rotation of the coil. Current induced in a circuit is given by the formula I is equal to I naught sin omega t plus alpha. Now for current, phase is omega t plus alpha. For EMF, phase is omega t. So there is phase difference between the current and EMF. Here I naught is the peak or maximum value of EMF, and as I told, alpha is phase difference between instantaneous EMF and instantaneous current. Here precisely the word instantaneous is being used because at instant t the current is I. At instant t EMF is E. So it changes with respect to time. Whereas peak value of the EMF remains constant, that is E naught. Peak value of the current remains constant, that is represented by I naught. If we graphically show variation of EMF with respect to omega t, what is omega t? Phase. So we are taking EMF on y-axis, of course instantaneous EMF, and on x-axis we are taking omega t. Minimum value of EMF is equal to 0 to begin with, means when the coil is about to start its rotation, that time phase is omega t, that is equal to 0, there is no EMF generated. When coil completes quarter rotation, that time phase is pi by 2. When coil completes half rotation, phase is pi. When coil completes third quarter rotation, phase is 3 pi by 2. And when coil completes one complete rotation, the phase is 2 pi. And for that, with the help of equation E is equal to E naught sin omega t, if you obtain values of EMF for various phase values, the nature of the graph you will get like this. Here, when the phase is pi by 2, EMF has maximum value, and that maximum value of EMF we represent by E naught plus E naught, just to indicate EMF is maximum on one side. When the phase is pi, EMF reaches to 0 value. When the phase is 3 pi by 2, EMF is also peak value, but in the opposite direction. And in opposite direction, we represent it by minus E naught. So whether it is plus E naught or minus E naught, it is a maximum value of the EMF. Plus and minus sign indicate only that the induced EMF changes its direction, or they are in opposite direction. So here we have to keep in mind that minimum value of EMF is 0 when the phase is 0, pi or 2 pi. But the peak value of EMF is E naught when the phase is pi by 2 and when the phase is 3 pi by 2, but in opposite direction. So induced EMF varies sinusoidally with time. Why is the word sinusoidally used? Because variation is as like sine function. The direction of EMF is reversed after every half revolution of the coil. So this nature of the graph you get in half rotation, and the next part of the graph you get in next half rotation or revolution. This type of EMF is called alternating EMF because it is alternating in direction. In one half cycle, EMF is in one direction, in next half cycle it is in the opposite direction, and corresponding current is also called as alternating current. Alternating voltages and current go through all values between 0 and peak value in one cycle, hence their mean or average value over a full cycle is always 0. So we have seen in earlier graph which clarifies the things. Peak value of an alternating current or EMF is the maximum value of current or EMF in either direction. And that's why if you find average value over a complete cycle, it will be always 0. That's why whenever we find average or mean value, we consider only half cycle. So the average value of all the values of voltage or current over half cycle is called average or mean value of AC. Average value of sine theta in the range from 0 radians to pi radians is given by, here mod sign is there which represents average. So average value of sine theta is given by the formula, of course over a half cycle, is given by the formula average value of sine theta is equal to integration from 0 to pi of sine theta d theta divided by integration from 0 to pi of d theta. Here we have to read this as integration of sine theta with respect to theta, where the limits are from 0 to pi, and at the denominator it is integration of d theta, limits from 0 to pi. Integration of d theta, we also say that integration of 1 with respect to theta, limits from 0 to pi. Now according to the rules of integration, integration of sine theta is minus cos theta, and limits we write lower limit at the bottom, upper limit at the top, limits are from 0 to pi. And integration of 1 with respect to theta is theta, and limits are also from 0 to pi. Now we have to replace variable. What is variable here? Theta by upper and lower limit. So minus cos theta, initially we are replacing theta by pi, and in minus cos theta, afterwards we replace theta by 0. And that's why minus cos of pi minus Now we are replacing minus cos theta, where theta we are replacing by 0. And that's why minus cos of 0. To the denominator, theta we are replacing by pi, upper limit, minus theta replacing by lower limit, that is 0. So we get this average value of sin theta, it is equal to 2 upon pi. With this, you get value of average value of sin theta equal to 0.637. So average value of current or EMF is equal to 0.637 times its peak value. So average value of the current, which is represented by I average, is 0.637 times the peak value of the current, and average value of EMF is 0.637 times the peak value of EMF. Now the next topic that we have to discuss is root mean square value of alternating current. Now why this root mean square value is introduced? That is because again we know that the average value of current or EMF over a complete cycle is 0. And if you are using moving coil ammeter or moving coil voltmeter, then in that case average value over the complete cycle is always 0. And that's why we introduce the concept of root mean square value of the alternating current. So as said, a moving coil ammeter and voltmeter measure the average value of current and voltage applied across it. The average value cannot be used to specify on alternating current or voltage because its value is 0 over one cycle and cannot be used for power calculations. Therefore, we must search for more suitable criteria to measure the effectiveness of an alternating current or voltage. And the obvious choice would be to measure it in terms of direct current that would do the same work or produce same amount of heat as the same average rate as AC under similar conditions. The quantity heat is chosen as it does not depend upon the changes in the direction of the current. Heat depends upon the square of the current, which is always positive irrespective of the direction of the current. Means whether current is positive or negative, the square of the current is always positive. The equivalent direct current is called the root mean square value of the current. We have started with the chapter AC circuits, in which we have studied two types of currents, alternating current, direct current. We have also revised Faraday's laws of electromagnetic induction, Lenz's law, and after that we discuss about what is the mean value of the current and RMS value of the current. Thank you.
सह्याद्री वाहिनी, प्रत्येक घरासाठी, घरातल्या प्रत्येकासाठी.
Hello students, I am Dr. D.D. Kumbar, Department of Chemistry, Ferguson College, Pune. Today we are going to see the remaining part of unit number 12, aldehydes, ketones and carboxylic acids. From that we are going to see the physical states, boiling points and solubilities of carboxylic acids. Then reactivity of aldehydes and ketones. After that we are going to see the influence of electronic effects, that is the steric effects. Right now, we'll move for the PowerPoint presentations. Last time, we were looking for the dimer of acetic acid, that is 2 molecules of this acetic acid held by 2 hydrogen bonds. Okay. So here in this figure, you will observe that this is the CH3C double bond OH, 2 molecules of acetic acid are there. Okay. Now here that carbonyl oxygen and hydrogen from OH group. Okay. So here it is mentioned over here by the dotted line. Okay. Hydrogen carries the positive delta, that is partial positive charge, and carbonyl oxygen carries the partial negative charge. So there is a formation of bonding. It is shown by the dotted line, that is hydrogen bonding. Similarly, here also you will observe that OH, hydroxyl group from acetic acid, and here that carbonyl oxygen from the another molecule of acetic acid. So there is a formation of hydrogen bonding which is shown by the dotted line. Okay. So formation of hydrogen bonding in 2 molecules of acetic acid. Lower aliphatic carboxylic acids containing up to 4 carbons are miscible with water due to formation of intermolecular hydrogen bonds between carboxylic acid molecules and solvent water molecules. Okay. The solubility of carboxylic acids in water decreases with increase in molecular mass. Higher carboxylic acids are practically insoluble in water due to the increased hydrophobic, that is water heating interaction of hydrocarbon part with water. Aromatic acids like benzoic acid are also practically insoluble in water at a room temperature. Water insoluble carboxylic acids are soluble in less polar organic solvents like ether, alcohol, benzene, and so on. After that, next point, that is the polarity of carbonyl group. The polarity of carbonyl group originates from higher electronegativity of oxygen relative to carbon as well as resonance effects as shown in figure 12.4. Okay. Now this is a carbonyl carbon and carbonyl oxygen. This is a carbonyl group. Okay. So in figure A, you will observe that the carbonyl carbon carries the partial positive charge and carbonyl oxygen carries the partial negative charge. Okay. So in bracket you will observe that in figure B, that is the measure, the carbonyl carbon double bond oxygen. So oxygen carries the 2 lone pair of electrons. Okay. So it shows that resonance structures of this carbonyl group. Okay. So this carbonyl carbon carries the partial positive charge, that is, and here there is one bond and which is joined to the carbonyl oxygen carries the 3 lone pair of electrons. Okay. So carries the minus charge, partial minus charge. Okay. So this is a minor structure. So these 2 structures, structure B and structure C, both are the resonance structures of each other. Okay. Then after that you will find that next structure, structure D, this is the resonance hybrid. Okay. So this carbonyl carbon and carbonyl oxygen, they are joined by the one single bond over here, and after that one bond, that is, it is shown by the dotted line. Okay. So this is a resonance hybrid. Okay, this is a resonance hybrid. So carbon carries the positive charge and oxygen carries the negative charge. This is the resonance hybrid. So this is almost this stable structure is there, and because of this carbon and oxygen, so polarity is developed. Okay, polarity is developed, and therefore here the polarity of carbonyl group originates from the higher electronegativity of oxygen related to the carbon as well as resonance effects as shown in the this figure. Okay. The carbonyl carbon has positive polarity. Carbonyl carbon carries the positive charge. See the structure A. See the structure A. So in this, you will observe that carbonyl carbon carries the positive charge and carbonyl oxygen carries the negative charge. See the structure A and structure D. Okay, structure D. Therefore, it is electron deficient. So here, remember, The positive charge always shows that deficiency of electron, and minus charge, it indicates that electron rich center, okay. So as a result, this carbon atom is electrophilic, that is electron loving, and is susceptible to attack by a nucleophile. This is the nucleophile, okay. Reactivity of aldehydes and ketones. Reactivity of aldehydes and ketones is due to the polarity of carbonyl group, which results in electrophilicity of carbon. In general, aldehydes are more reactive than ketones toward nucleophilic attack. This can be well explained in terms of both the electronic effects and steric effect. The first effect, that is influence of electronic effects. So alkyl groups have electron donating inductive effect, that is plus I effect. Okay. A ketone has two electron donating alkyl groups bonded to carbonyl carbon, which are responsible for decreasing its positive polarity and electrophilicity. In contrast, aldehydes have only one electron donating group bonded to carbonyl carbon. This makes aldehydes are more electrophilic than ketones. So simply remember that in aldehydes and ketones, the functional group for the aldehyde, that is RCHO, and for the ketones, RC double bond OR dash. Okay, so means in aldehydes there is only one alkyl group which is attached to the carbonyl carbon, and in ketones there are two alkyl groups which are attached to the carbonyl carbon, and therefore here aldehydes are more reactive than ketones. Steric effects. Two bulky alkyl groups in ketones come in the way of incoming nucleophile. This is called steric hindrance to nucleophilic attack. Steric hindrance means actually crowding. That is known as a steric hindrance. On the other hand, nucleophile can easily attack the carbonyl carbon in aldehyde because it has one alkyl group and is less crowded or sterically less hindered. Hence, aldehydes are more easily attacked by nucleophiles. So, we'll see in this figure, okay, this is a ketone and this is an aldehyde. So, as I told that earlier, carbonyl carbon which is attached to the oxygen, and here two alkyl groups which are attached to the carbonyl carbon, okay, carbonyl carbon. And in aldehydes, only one alkyl group is attached to the carbonyl carbon, okay. So, carbonyl carbon carries the positive charge and carbonyl oxygen carries the minus charge, okay. So, in ketones and aldehydes. Then next property, that is the chemical properties of aldehydes and ketones, okay. The laboratory tests for aldehydes and ketones. Aldehydes are easily oxidized to carboxylic acids and therefore acts as a reducing agents. Toward mild oxidizing agents, ketones do not have hydrogen atom directly attached to carbonyl carbon. Hence, they are not oxidized by mild oxidizing agents. On the basis of this difference in the reactivity, aldehydes and ketones are distinguished by the following test. Okay, the test given by only aldehydes, that is Chip's test or Chip's reagent. When alcoholic solution of aldehyde is treated with few drops of Chip's reagent, pink or red or magenta color appears. This confirms the presence of aldehydic, that is bond CHO group. Okay. Then next, second test, Tollens test or silver mirror test. When an aldehyde is boiled with Tollens reagent, ammoniacal silver nitrate, silver mirror is formed. The aldehyde is oxidized to carboxylate ion by Tollens reagent, and Ag plus, that is Ag plus ion is reduced to Ag. Okay. We'll see about the reaction RCHO. This is an aldehyde. Okay. Plus, when it is reacted with the twice AgNH3 twice plus thrice OH minus. Okay. So collectively this is known as a Tollens reagent. When it is heated, after heating it will give the R bond C double bond O minus, that is a carboxylate ion it is obtained, plus twice Ag, okay, twice Ag, that is the precipitate is obtained, that is the silver mirror, okay, plus 4 NH3, evolve the gas, that is ammonia gas, and plus twice H2, water molecule, okay. If you see that example with the acetaldehyde, okay, CH3CHO, if you have taken the acetaldehyde, CH3CHO, when it is reacted with the Tollens reagent after heating in water bath, so you will observe that CH3COO minus, that is carboxylate, that is acetate ion is developed, okay, acetate, and plus you will get the twice Ag plus 4NH3 plus twice H2O. So this is the Tollens reagent, that is the silver mirror test. After that, next test, that is the Fehling test. When a mixture of an aldehyde and Fehling solution is boiled in hot water, a red precipitate of cuprous oxide is formed. An aldehyde is oxidized to carboxylate ion by Fehling solution, and copper 2 plus ion is reduced to copper plus ion. It may be noted that alpha hydroxy ketone also gives these tests positive. So this is the aldehyde RCHO plus twice Cu2 plus 5OH minus. Collectively it is known as a Fehling solution. After boiling, you will get the, that is carboxylate ion R bond C bond COO minus plus Cu2O, that is the precipitate you will get, that is the red PPT, and plus thrice H2O. We'll take one example. When the acetaldehyde CH3CHO, when it is treated with the Fehling solution, after boiling you will get CH3COO minus, that is acetate ion you will get it, okay, plus Cu2O, that is red PPT, and plus thrice H2O. So it means that Fehling test. Now this laboratory test for the ketonic group by the sodium nitroprusside test. So this year, only this year, this part of the syllabus is omitted. Just see the slide only. What are the reactions? Okay, next property we'll see, that is chemical reactions of aldehydes and ketones with nucleophile. In all these reactions, the nucleophilic reagent brings about reactions by attacking on positively polarized electrophilic carbonyl carbon in aldehydes and ketones. Okay. Then addition of hydrogen cyanide, that is HCN. Hydrogen cyanide, that is a weak acid, adds across the carbon-oxygen double bond in aldehydes and ketones to produce compounds called cyanohydrins. The negative part of the reagent, that is bond CN, attacks the electrophilic carbon of a carbonyl group. The reaction requires either acid or base as a catalyst. So directly we'll see the reaction. This is the ketone RC double bond O R dash. R and R dash both are the here are the different alkyl groups, plus HCN, hydrogen cyanide. It gives R dash CR bond CN bond OH. It is known as a cyanohydrin. It is known as a cyanohydrin. So aldehyde, when if you are taking the aldehyde, when R dash is equal to H. When you are treating aldehyde, then R dash may be the hydrogen. And when you are treating ketone, that R dash may be the alkyl or aryl group. Alkyl or aryl group. Okay. For example, we'll see the example with the acetaldehyde, CH3CH double bond O plus HCN. So directly addition takes place over here. You will get that CH3 C bond R bond OH bond CN. Okay. That is acetaldehyde cyanohydrin. Acetaldehyde cyanohydrin. Another example with the acetone, that is ketone, CH3C double bond O, C bond CH3, okay, plus HCN, addition will take place here, you will get CH3 bond C bond OH, bond CN and bond CH3, that is acetone cyanohydrin. So addition of HCN takes place in this way. Then addition of sodium bisulfite, NaHSO3. Aldehydes and ketones react with saturated aqueous solution of sodium bisulfite to give crystalline precipitate of sodium bisulfite adduct, that is addition compound. For example, we'll take the example of acetaldehyde, CH3CH, C double bond O plus NaHSO3, sodium bisulfite. So addition will take place here and you will get CH3C bond OH, bond H and bond SO3Na. That is the acetaldehyde sodium bisulfite adduct. Okay. This is with the aldehyde. Another example we will see with the ketone. CH3C, CH3, C double bond O, that is acetone. When it is treated with NaHSO3 sodium bisulfite, after the addition, it gives that CH3C bond OH bond SO3Na bond CH3, that is acetone sodium bisulfite adduct. So such a way addition takes place. Then addition of alcohols. Aldehyde reacts with one molecule of anhydrous monohydric alcohol in presence of dry hydrogen chloride to give alkoxy alcohol known as hemiacetal, which further reacts with one more molecule of anhydrous monohydric alcohol to give a geminal dialkoxy compound known as acetal, as shown in the reaction. Okay, so step 1. So this is the aldehyde RCH C double bond O plus R dash OH. Okay, this is an alcohol. Okay, aldehyde is an alcohol. So this is the reversible reaction when it is treated with the dry HCl. Then you will observe that you will get here hemiacetal, RC bond O, R dash bond OH and H. Okay, that is hemiacetal. That is unstable product. This is an unstable product. Another, that is the step number 2, that is RCH bond OH bond OR dash, okay, plus R dash OH, that is alcohol. So here this is the reversible reaction, dry HCl. After that you can treat with the dilute HCl. You will observe that RCH bond OR dash bond OR dash, okay. So in a step 1 there is a single alkoxy group, and in step 2 the product there are two alkoxy groups are there, okay. So when there is only one alkoxy group, that is known as a hemiacetal, and when there are two alkoxy groups, then it is known as a acetal, okay, acetal, and plus water molecule it is formed. So in this reaction, that acetal, when it is treated with the dilute HCl, then you will get the hemiacetal, okay. Similarly, when the hemiacetal, when it is treated with the dilute HCl, then you will get the aldehyde. So therefore these are the reversible reactions. These are the reversible reaction. For example, here we will see that step number 1, that is acetaldehyde, CH3CH C double bond O plus C2H5OH. This is the ethyl alcohol. This is the ethyl alcohol. When it is treated with the dry HCl, okay, dry HCl means free from water molecule, then you are getting CH3CO C2H5O bond OH and bond H. That is hemiacetal unstable product, okay. So there is only one alkoxy group, that is the ethoxy group, C2H5O, that is the ethoxy group is there. So it is known as a hemiacetal. Then when this hemiacetal, when it is treated with the dilute HCl, then you will get the original product, that is acetaldehyde and alcohol, okay. In a second step, this hemiacetal, when it is treated with the another molecule of ethyl alcohol, C2H5OH, when it is treated with the dry HCl, then you will get here CH3CH C bond O C2H5O bond O C2H5O plus H2O. So here you will get the 1,1 diethoxy ethane, that is the stable product. In this product, this is the acetal, okay. In this product there are two alkoxy groups, that is two ethoxy groups are there. Two ethoxy groups are, so therefore it is known as a acetal. And when this acetal, when it is treated with the dilute HCl, then you will get the hemiacetal, okay. Similarly here also hemiacetal, when it is treated with dilute HCl, then you will get the acetaldehyde. So therefore these two reactions are the reversible reaction, okay. Similarly, ketones react with alcohol in presence of acid catalyst to form hemiketal and ketal. Ketones react with 1,2 or 1,3 diols in presence of dry hydrogen chloride to give 5 or 6 membered cyclic ketals. So this is the ketone RC double bond O R, that is a ketone. Plus, if you are treated with the CH2H, that is ethylene glycol. So IUPAC name ethane 1,2-diol. When it is treated with the dry HCl means free from water molecule, then you will get here RC bond R. Here you will get C carbon, it is attached to the oxygen, bond CH2 bond oxygen and this carbon. Okay, that is cyclic ketal is obtained. What you are getting? Cyclic ketal is obtained. Ketal, why it is called as ketal? Because it is obtained from the ketone. Okay, cyclic ketal. So when it is treated with the dilute HCl, then you will get the reactants. Original products you will get it. Okay. Now, the reaction can be reversed by treating the cyclic ketal with aqueous HCl to regenerate the ketone. Acetals and ketals are hydrolyzed with aqueous mineral acids to give corresponding aldehydes and ketones respectively. Then next reaction, addition of Grignard's reagent. Aldehydes and ketones on reaction with alkyl magnesium halide followed by acid hydrolysis give alcohols. Refer to chapter number 11, section 11.4.1d. Okay, the previous chapter you will see that. So this is the ketone when it is reacted with the Grignard's reagent RMJX. Okay, so you will observe that here that from the Grignard's reagent R carries the that is the alkyl group carries the negative charge. Okay, and that magnesium metal carries the positive charge and halogen carries the negative charge. Okay, and carbonyl carbon carries the positive charge over here. So that alkyl group R, it is attacked on the carbonyl carbon. Okay, after that when it is treated with the dry ether, then you will get the complex that is the bond C bond OMGX bond R. Okay, this is unstable product is formed. After the acid hydrolysis, you will get that bond C bond OH bond R plus MgX and MgOH. Okay. For this purpose, we will take one example over here. We will take the example with the acetone and CH3 C double bond O CH3, that is the acetone. Okay, plus you will take the methyl magnesium bromide CH3 MgBr. When it is treated with the dry ether, then you will get here CH3 OMgBr. Okay, on acid hydrolysis you will get here CH3 and OH plus Mg, Br and OH. The name of this alcohol, it is known as a tertiary butyl alcohol. You will get the tertiary butyl alcohol. Then nucleophilic addition, elimination of aldehydes and ketones with ammonia derivatives. Aldehydes and ketones undergo addition elimination with some ammonia derivatives, that is NH2 bond Z, to give product containing double bond carbon double bond N bond, that is the imines. The reaction is reversible and takes place in weakly acidic medium. The substituted imine is called a Gibbs base. So this is the reaction here, aldehyde or ketone, carbon double bond oxygen plus NH2Z, which is reversible in bracket, that is square bracket, that is unstable product, that is carbon bond OH bond NZ bond H. Okay, when water molecule is eliminated and it gives the carbon double bond nitrogen bond Z plus H2O. So carbon double bond nitrogen bond Z, it is known as a imine. It is known as a imine, where Z is equal to that is alkyl group R, aromatic group NH2, NHC6H5, NHCONH2, NHC6H3NO2 twice. For example, we'll take here example, that is the acetaldehyde CH3 C double bond O CH plus NH2OH hydroxylamine. A reversible reaction takes place and you will get that CH3 bond C bond H bond N bond OH. So nitrogen is attached to the hydrogen and here this carbon is attached to the OH. Okay. So in your textbook, there is a printing mistake for this structure that carbon, it should be attached to the one hydrogen. But hydrogen, it is not given in your textbook. Please, everybody, please make a correction in your textbook for this example and this reaction only. Okay. So after elimination of water molecule, you will get here CH3CH, C double bond, N bond OH. That is the acetaldoxime. You are getting acetaldoxime. All aldehydes and ketones give similar reactions. Some important reactions are listed in table number 12.7. The resulting products have high molecular mass and are crystalline solids. These reactions are therefore useful for characterization of the original aldehydes and ketones. So this is the table number 12.7, nucleophilic addition, elimination reactions of aldehydes and ketones with ammonia derivatives. Today we have seen the unit number 12, that is aldehydes, ketones and carboxylic acid. From this unit we have studied the solubilities and boiling points of aldehydes and ketones and some influence of electronic effects on aldehydes, ketones and carboxylic acid. Thank you very much.
सह्याद्री वाहिनी प्रत्येक घरासाठी, घरातल्या प्रत्येकासाठी.
भारत के कोने कोने से फिजाओं में गूंजती विविध भारती,
देश की सुरीली धड़कन
विविध भारती, भूले बिसरे गीतों के साथ संगीत सरिता.
कुछ बातें कुछ गीत, कायम रहे छाया गीत.
तलाश करती इंस्टाग्राम, फेसबुक, मायने रखते हैं आपके ट्वीट.
वीर सैनिकों की जयमाला
और हंसी का हवा महल. बाइस्कोप की बातें, यादों के उजाले.
चौबारे पर सहेली है सखियों के संग.
सखी सहेली,
बॉम्बे टॉकीज और
सेल्यूलॉइड के सितारे.
हम क्या कहें, आपको याद सब है जरा जरा.
मुझे याद सब है जरा जरा.
और आपके अपने लोकल रेडियो स्टेशन पर,
DTH और ऐप पर 24 घंटे 7 दिन.
मन का सुकून, दिल की आरती.
सुरीली संदली